first speaker is Jiayao Shao, who will talk about stochastic dynamical system methods applied to ship capsize problem. The floor is yours. Thank you.
Thank you for introducing me. And I've seen familiar faces in the audience. So I've presented these topics in both BAMC and SIAM before. So if you're familiar with spoken before, this is going to be quite similar to previous talk, but I have new results at the end. So yeah, and for new faces, let me share this great idea with you guys. So here I say I want to show or share the stochastic dynamical system methods applied to ship capsize problem, meaning that I want to illustrate the method itself with a ship model, but it doesn't mean that this can be only applied to ship model, and it can be, and we expect this to be applied to a wider application scenarios. Okay. So just some overview. Okay, so we want to answer some questions like why a ship would capsize, what is the probability of capsizing, and if the ship capsizes, how will it capsize, and what is the expected capsize time? And we will try to answer these 4 questions in the following talk. Okay, now let's try to understand the first question, why a ship would capsize. So that's a ship model. That's a smaller version of the ship model here in my hand. So for a ship, we have 6 degrees of freedom, and we pick only 2 degrees of freedom in my case, which is the row, and the heave. And we image that the scenario is like you are in a kind of water that the water wave is going perpendicular to your ship. So when the wave pushes your ship from this side, you can imagine it push the ship from its stable point like here, rotate a little bit, and then since the wave is like you have cross and trough, you lift the ship a little bit up and then drop down. It's this kind of motion. Okay, so we see that these 2 degrees of freedom are involved in this kind of dynamics that you roll in some angle, you lift it up in the heave direction and do this kind of motion. So that's kind of equation that governs this kind of coupling between heave and roll. Okay, some math calculations to change that to first order differential equations. So that's the dynamics for the ship. We notice that when we try to analyze this system, we have 3 critical points. The first critical point is the stable equilibrium. I can assume everyone has some back knowledge from. Yes. So we have a stable equilibrium like here, where we have no roll, no heave, just in steady water, shipping steady water, and we have 2 saddles. Those 2 saddles corresponds to where the ship loses its stability. Like when the wave is too large or the force is too large, the wave goes like here, and they capsize. But we see that the whole unstability is from the roll direction, not from the heave direction. Like suppose we have no roll at all, no matter how high you got lifted up, you don't lose your stability. But say, for example, if you are tilted for 90 degrees, you lose your stability. So we have 3 critical points. 1 corresponds to the stable equilibrium like here. 2 saddle corresponds to the symmetric capsize angle. So we notice that without any external forces or without any external wave, the ship won't capsize at all. It will just stay at its original position, or say stable equilibrium forever. But the noise or the external perturbation is what makes the ship capsize. So we try to add noise on top of the ship dynamics. And here we emphasize 2 properties of the noise that is added to the ship. First of all, the noise is degenerate. For degenerate, we mean that the covariance matrix is singular. It's not invertible. Why is that? So here's some physics knowledge here, that we know the moment is the rate of change of configuration, meaning that once we know the configuration, we take derivative with respect to time, we know its momentum. So basically that means one dimension is fully determined by the other by taking derivative with respect to time. So if we add noise on both momentum and configuration, this is not very realistic method. We add noise on only one component and the other is fully determined by that. So back to our dynamic equations, we add noise to only to momentum dimensions, not to configuration dimensions, because those two, like I know one, the other one is determined. That makes the noise, first of all, degenerate. And the other point of the noise added is that it's filtered. Let's see what is a filter noise. Here is the comparison between what Gaussian noise, so basically Brownian motion, and Brownian motion after filtration. So we see that after filtration, the noise is not much more smoother than before, but smoother than before. Like previously, it's very sharp and short periods for like high frequency, which we know that in real life, the wave can't be really like the above figure, but more like the below one, that is with longer period, less sharper and smoother. So here we see that the dynamics of the ship has the first four UVXY from the ship itself, and two more psi1, psi2 for the added filter noise, which help make this overall question a 6 degrees than ODE. Okay, so now we have answered the first question. Why should we capsize? Because we have external disturbance from the wave, from the wind, that caused the ship to capsize. And we also emphasize here that the noise added to the ship is filtered and degenerate. The next question, what is the probability of capsizing? So here we use large deviation principle to model the probability. We have the very famous central limit theorem that describes most of the scenarios, but central limit theorem is not applicable here because central limit theorem is usually used to describe a very medium-centered or say mean-centered situations that we focus most of the thing around the mean of the probability distribution. But ship capsize is a rare event. We don't have sizing all the time, every day, right? So it's a tail event, which should have a rare probability or very small probability rate. So we use this large deviation principle to describe the probability rate, where if we want to observe such kind of event, capsize event, the probability scales like exponential to a minus s over epsilon, where epsilon controls the strength of the noise added. And what is s? S is a functional called rate functional, taking this form here. So it depends on the dynamics, the difference between the deterministic, so our dynamic is phi dot is b phi plus some noise. So phi dot minus b phi is just our noise part. So basically, if we understand this from an energy perspective, it means that how much or what amount of energy do I need to make this happen? And this energy controls my probability. Okay. And here we notice one problem. In the expression of our rate functional s, we notice that we have an inverse of A, where A is the covariance matrix. But remember, we mentioned that the noise is degenerate and filtered. Degenerate means the covariance matrix is singular, meaning that it's not invertible. So this is, in our case, a well-defined rate functional. How can we do that? how can we fix that problem? We try to use a method called Hamiltonian method by introducing a new parameter theta that we change the expression with a minus 1 here to, so we multiply a on both sides so that a theta is phi dot minus theta. Then we change our action function to this form here that we don't need to involve a lot of, we don't need to involve inverting the covariance matrix. And on the other hand, since A is the covariance matrix which we say is singular, it means this A should have a lot of zeros in it, meaning this is actually of very low dimension compared to our original SIAM-IMA question. Okay. So we have kind of solved the second question. What is the probability of capsizing? It's governed by this large deviation expression, which the probability is determined by some rate function of S, or we can understand this by some energy that required to push the ship from stable equilibrium to capsize. And we want to find the optimal trajectory phi star such that this is the smallest value. So if we think about the probability, here. So the probability is like e to the power of minus something. If we sketch a graph of e to the power of x, we see that when the power is negative, the smallest, for smallest I mean absolute value. So the smallest rate function of s is, the greater the probability we can observe. And we want to find the event that gives the largest probability, because since all of the events are so rare that it is already very hard to observe even one event. So once one event is observed, that is usually the most likely event on the tau. So we just want to find the most likely event for the rest of the events that are even rare and even hard to observe, and it's even hard to model. Okay, so we want to find the smallest action S, giving the largest probability P that we can observe. And that trajectory, we say, it's the optimal trajectory to observe, to make the ship capsize. Okay, so we've answered the second question, and luckily we also answered the third question. The large deviation helped us describe the probability, and the way that we find the minimum rate function of action, we call it action, gives us the optimal trajectory phi. So the phi itself describes how the ship capsizes. And the last question is, what is the expected capsize time? So the thing is, we have the system looks like this, where this is our stable equilibrium and these two saddles are the capsize angle. Usually when we numerically model this kind of behavior, we go from this lowest point, we add noise to it, try to push, so similarly to this kind of model, try to push this ball away from this sink to this point here. And we can imagine that a lot of energy or computational energy is wasted around these areas, because if the noise is very, very small, you spend a lot of time just swinging around these areas. And similarly for here, you spend a lot of areas, time, energy around here. And what we actually care is how we go from, say, here to here. This is like the effective transition time. But other than these, this specific area, the time spent around here and time spent around here are not so meaningful. So how do we deal with this kind of problem? We chop the overall transition process into three parts. The first part is to escape these small area, we call it vector function. And the second part is what is actually the effective escaping process. And the third part is how we finally go into the saddle. Okay, so that's what I described here. Is get 1 to 3 steps, escape from the maximum attraction, the effective transition, and reach the capsize region. Okay, so the expected capsize time is that what we care is about how much time is spent here. But usually, if for any system, if you give it long enough time, it will eventually capsize. Okay. And some results. So is that too small? We can try to read or understand what's going on in the figure. So we see on the top left corner that red line is the effective transition part. And if we enlarge the top left figure a bit, we give the bottom left figure where the pink and the red are the connection points from phase 1 to phase 2. So we see the x-axis is the row and the vertical axis is the heave. Then we can directly read all the dynamics of the ship. We see that it's going something like this, right? So x-axis is the row. Then what the ship is doing in this case is that it spent a lot of time just repeating this kind of motion, up and down a little bit, and we see that the angle is getting larger and larger and larger until one point it goes from the pink to the red that is too large. Then it pushes the ship away, following the red curve to the point near the saddle, and it capsizes. Okay. And I compared 2 different graphs here for different time t. So the time t here is the effective transition time t here. What I want to show by comparing these 2 figures is that by given 2 different effective transition time, I actually get very similar final answers. So similar actions, meaning that the probability should be rather similar, and similar capsize trajectory. They are all doing this kind of swing until capsize. And the key point or the key idea here is that by using our method, by chopping the whole process into 3 parts, we save a lot of computational costs on allowing by giving the total time t. So to just simply explain this, if you want to replicate or to repeat the experiment or to apply the experiment to real life, you want to give it longer and longer times so that it's more realistic. But by giving the computer longer time, it means the computer needs more power to give you the answer. But in my case, even though the time is given longer, I have rather similar results, meaning that by using this method, I can actually save a lot of computational energy to get the true result by linearize the dynamics around phase 1 and phase 3. And I think one more result here, an interesting result. So what's going on here is that since we should have different type of ships and the way of heave and row coupling are different for different ships, this is by comparing how the probability changes for different ship for different way of coupling heave and row. And we see that the different coupling would give different action, meaning should have different probabilities. And the lowest point is attained roughly at 1.2, and the maximum or the biggest value is roughly obtained around r equals to 1.8. How can we understand this minimum value and maximum value? If we compute in the large deviation equation and compute the difference, we see that under some small noise, epsilon, say epsilon is 10 to the power of -4, then the difference between capsize for the smallest point to the biggest point is roughly 6 to the power 6 times 10 to the power of 6. So like 100,000 difference in probability. So this is just to show a slight change in the shift under the limit of small noise would make a huge difference on the probability forecasting. Yeah. I think that's everything. And that's the reference. Thank you very much. Okay. Thank you very much. We had questions?
I had one question earlier on. When you said you had the technique for getting rid of, for handling the fact that your noise was degenerate, and I was wondering intuitively what's that getting around, because you would be dividing by something by 0. Presumably it would have to be a 0 division by 0 to not actually get some infinite blow up, and then sort of intuitively, what does your trick? Yeah, what would the equivalent be? Would it be equivalent to using just the more polymerase pseudo inverse, where you just invert the non-zero eigenvalues, or is it something else?
Something else. So I actually avoid inverting anything in my method. So since like we have the action functional, this is the noise dw. dw, some sigma dw. So previously, the method to measure the energy or the action is phi dot minus v phi with a minus 1 similar thing here. So basically, this one minus this one, we left with only the noise. But instead of expressing this whole part as this minus this, we directly model or evaluate the value of sigma transpose dw. Well, this is not a very rigorous math equation, but we directly evaluate this part itself rather than expressing this part as this minus this. So then directly evaluating here, we don't need to do any inversion. So there's no inversion of singular matrix at all.
Okay.
If that answers.
I think so. Yeah, I'll think about it some more as well. But yeah, thank you.
Any other questions?
Yes.
In your action, your S, you have sort of a time horizon, a capital T.
Yes.
What does that represent?
So that is by understanding from this model, the big T. So basically, we set time T here. The timing of escaping from the basin of attraction, we give it time 0, so that's like the starting time, and the time of going into the settled area is the big T. So we measure the action I mentioned is measuring the energy required to go for this transition area. But actually, the overall question is adding everything from this part, and these.
One more. Sorry, on that question of splitting it into 3, how do you decide where the boundaries go?
Oh,
and could you split it into more, or is it something specific about these points?
You mean split into more? You mean chop into even more?
Yeah, I've seen other rare events things where they just split it into tons of things, and they say, oh, okay, conditional on the probability of being here, what's the probability of doing the next step? So is it that, or is there something more specific going on?
In this specific case, it splits only into 3. And how do I decide the boundaries? Is that imagine you are the little ball staying here. So you actually tend to, because the deterministic flow will trap you in this region. So it's not hard to determine the boundary around basin of attraction because the ball tends to stay around here. But the ball doesn't want to go here because it requires energy. So what we do is that we define a region, say a sphere or an ellipsoid, around the saddle, and we let the ball choose where does it want to lay on this sphere. And the point where the ball lies on the sphere is the optimum point that gives the smallest action. So the starting, say connection points from this section to this section is we let the ball choose itself. And for this area, we define an area that is close enough to the saddle so that it can go, we can guarantee it go into the saddle, but it can choose on which point to stop. So basically, it spirals out, connection point, effective transition on the ball, and they pick which point to stop on the ball. And for whatever inside the ball, we linearize the dynamics.
So basically, if you've got the linearized dynamics or the non-noisy one or something, then it's really easy to determine what radius those balls should have.
You mean for this one?
I guess the left one first, but maybe if they're different, are they different then?
They're
Okay.
treated differently.
Maybe I'll talk to you later.
Yes.